Welcome to my cycle tempo tutorials. In this tutorial, we will calculate a Brayton cycle and a combined cycle consisting of gas turbine and bottoming steam cycle. We will start with a simple Brayton cycle. The Brayton cycle will consist of following components. We will need a turbine, a compressor, we will need a combustion chamber, combustor, and we will need our air inlet, fuel inlet, and flue gas heatsink. Now we can connect the components together, where the gas as the fuel inlet will go into the combustor, and note to connect it into the inner circle. We can also consult the reference guide, where we can search for the combustor. And here you can see that we have oxidant inlet at the outside, while the fuel inlets are, or both solids or gas are at the inside. Then exhaust is from the outside. That's the gas. Then we will have flue gas going out of the combustor into the turbine and into our sink. And we will need air. I missed it. Air going from our source of the air into the compressor and as oxidant into the combustor. Now setting up the parameters. So our sink for our working fluid at the outlet, we will need to specify inlet pressure, which will be 1 bar, basically 1 atmosphere. Also the source of the air will be at 1 bar, so P out 1, and we will need to specify temperature of the air going into our cycle, which we can put 15 degrees C. Then for the compressor, we will need to specify isentropic efficiency. Let's put in 0.75. Similarly, it goes for the expander. Let's have 0.88. Now let's specify the fuel inlet, where the outlet pressure will be 30 bar, 3 megapascal, high pressure fuel line, and outlet temperature, standard conditions, 15 degrees C. Okay, now what else we need to specify? We will need to specify our combustion chamber, our combustor. As most of the components, we will need to specify some pressure drop. Let's put in 0. We haven't specified in our problem inlet pressure at the outlet of the compressor, so we can specify it here. Let's put in 20 megapascals, 20 bars, meaning pressure ratio of 20. And let's specify outlet temperature of combustion 1300 degrees C. Now we will also need to specify the EEQ code, the code for the way we want the combustion chamber to calculate. Again, let's have a look into our reference guide of what does it mean. And here we have mentioned that depending on the energy equation, the EEQ code, there are two possible ways using the energy balance. If we put in 1, so energy balance can be used to define a mass flow, while if we put in 2, which is default, the energy balance will be used to determine outlet temperature. So, in our problem, we want to have specified outlet temperature and we want to calculate the required mass flow rates of the oxidant and fuel. So we will need to put in EEQ code equals 1. One more thing that we haven't specified yet, we need to say to the program what are the compositions of our working fluids. So here at the airline, let's put in add composition and choose standard air. And at the fuel line, let's also add composition and put in standard natural gas. Now, if we would run the problem, so we would get one error. The one error saying that we are missing one more equation in the system. That is because we haven't specified the mass flow rate or power output of either mass flow rate of fuel or the air as oxidant or the power output. So we will specify our power output, so general data production function, and apparatus number 1 will have power of 50 megawatts. Now we have still few more issues. We don't know the temperature after the turbine. Then we can have a look at the turbine and we see the mistake that actually we put in the eta mechanical instead of eta isentropic. So once we fix this, our problem can run with 2 warnings. Always you need to have a look at the warnings. What do they say? Whether you can ignore them or not. You remember in last problems the warnings were sometimes about crossing of temperature profiles, so that is warning that cannot be ignored. However, here there is the warning using pre-estimated value for oxidant and fuel ratio in the first apparatus is applied, and based on that is calculated are calculated mass flows. And this warning happens only in the iteration number 0, and in following iterations of the problem we don't have any of these warnings. So the warning can be ignored and our problem is calculated. Now we can have a look at the system efficiencies, and we can actually see that the net efficiency is about 34% and gross efficiency 86%. Here we will demonstrate what does it mean and how does the program take the gross and net. The gross efficiency is only efficiency of the power producing equipment, which here is our turbine, and there is nothing connecting to it. If we modify our problem and let's say take a shaft that connects through these 2 pieces of equipment and run the problem again, so we can see that the gross and net efficiencies are the same because there is no other parasitic load that wouldn't be connected to the power producing equipment, to the turbine. Lastly, to have a look at parameters in our system, so we can, for example, see at the combustion chamber that we have the airflow at temperature of 500 degrees C after the compressor and mass flow rate of 55 kilograms per second combined with 1.5 kilograms per second of fuel, and we get flue gas with the temperature of 1300 degrees C. Now, in the second part of this tutorial, we will make a model of a combined cycle. So our combined cycle will start with a gas turbine, where we will use already given gas turbine component, which is provided in the cycle tempo. And at first we can just run our gas turbine, connect it to the stack, set inlet pressure 1 bar, and for our gas turbine, let's select some gas turbine of whichever you would like. For me, let's say I will take this one from Siemens. And now we have a running model of already predefined gas turbine, where we can see the flue gas has temperature of 527 degrees C and given mass flow rate. Now we will, however, want to put there some heat exchangers so that we can recover the heat and create more electricity. Currently, the gas turbine itself produces 190 megawatts. So we will want to add some heat exchangers. Let's put there for now 2 of them. Connect them so that the hot side is the secondary side. And one of our heat exchanger will be the superheater, from which the steam will go into the turbine. Like this. The other one will be our boiler or evaporator, where the steam will be made by circulating the working fluid, the water, between this component and drum. We will consider a system with natural draft circulation, so there will be no pump between the water outlet of the drum and the inlet of our evaporator. And then the returning steam will be returning back into the boiler. Make sure to connect the ports of the into the drum. Make sure to connect the ports of the drum correctly, because as you can see in the reference guide where we search for the drum, so we have the inlets and outlets of the main flow in the upper part of the drum, while inlets and outlets of the circulating flow at the lower of the circulating flow are at the lower part of the drum. So that's our circulating flow, getting the steam in our saturated steam at our system. The steam is connected to the superheater. And now for the other parts of the steam cycle, so we will need a condenser after the turbine. We will need cooling circuit. Let's make it nice. So steam goes from the turbine into the condenser, where it condenses, and then pump. Condensate pump increases the pressure, but for our system to work we will need also the aerator. So the water will go from the pump into the aerator, and then we will have main feeding pump where the pressure will be increased and the water will go into the drum. And of course the aerator has to be heated up by the steam bleeding from the turbine. Now setting up the components parameters. So let's start from the cooling circuit. Outlet pressure 1 bar, delta P pressure drop across the component, let's put 0, outlet temperature, let's put in 20 degrees C. Now let's go for the condenser, where we will specify again delta P, both at primary and secondary part 0, and we can specify the condensing pressure directly, so let's say 0.04 bars for kilopascals. The minimum temperature difference at the hot side of the condenser will be 5 degrees C, and for simplicity we will not have any subcooling at this point. Then we have a pump where we just need to specify isentropic efficiency. Then the water goes to the aerator, where we need to have delta P and temperature at which the thermodeaeration takes place, 105 degrees C. Now we have a pump where we will specify where we will again need to put in the isentropic efficiency, and we can use this pump, this component, to specify the evaporation pressure in our cycle. So we can put 18 megapascals. Now we move on to the drum, where in the drum we need to specify only the circulation ratio in our case. So we can put the circulation ratio as 3. And finally we go for the heat exchangers. So we have 2 heat exchangers here. First the number 4, the evaporator. Here we need to specify the pressure differences, so let's put 0, 0. Delta T at the low side of the heat exchanger, let's put 10 degrees C as the pinch point, and let's put EEQ code number 2 in here. One of these as we have the system of 2 heat exchangers, so one of them will have to be used as the one for calculating the mass flow rate in our cycle, and the other one will only follow and will be used just with one energy equation to calculate the outputs. So we put number 2 in here, and we put number 1 as EEQ code in the heat exchanger for the superheater, heat exchanger number 3. Again pressure drops, so 0 and 0, and at this heat exchanger we will need to specify minimum temperature difference, where the valid point where to specify it, if you consider how the Qt diagram looks. So it's at the high temperature side of the heat exchanger, and as it's in the gas phase, so we put a little bit larger value. Let's put in 35. So now we have most of the system specified, but we still have 2 errors. We can have a look at them. And the problem is that we cannot get temperature in pipe number 10 and pipe number 15. And that is because we forgot to put in the isentropic efficiency of the turbine. So let's put 0.88. And now the turbine can calculate, only we got quite a large number of warnings. So let's have a look at our messages, what the warnings are about. And we have negative mass flow rate in some of the pipes. Actually, looking at the number of pipes, where is the negative mass flow rate, so we can see that it's the whole steam cycle. So this clearly is some numerical calculation issue. So what we can try to do is to change which of the heat exchangers is used to calculate the mass flow rate. So instead of the heat exchanger 3, where we switch the EEQ code to number 2, in the heat exchanger number 4 we switch it to number 1. Now calculating the problem, we don't get any warnings nor error, and we can have a look at the view, new graph, Qt diagram, and get the Qt diagram of these 2 heat exchangers, so number 3 and number 4. And we can see how the Qt diagrams work and how our fluid is heated up and superheated. Now we can have a look how much extra power did we get. So on top of the original 190 megawatts, we get another 40 kilowatts by this turbine. Looking at the system efficiencies, so we achieved increase of efficiency from 36% to almost 44%. Now looking at either the Qt diagram at the temperature of the cooled down flue gas, or specifically looking at the inlet of the chimney, we can see that our flue gas cools down only to 367 degrees C, so there is still lots of energy remaining. What we can do with that is to add another heat exchanger, preheater, or also called economizer, which will be placed for the steam cycle downstream of the drum. So let's add the heat exchanger, connect it to the flue gas, and connect the water from our feeding pipe nice. So again, now so now we have another heat exchanger. Let's again put in 0 pressure drops. EEQ code number 2, because we already have this heat exchanger specified to calculate mass flow rate in our steam cycle. And let's specify delta TH, where we can put 15 degrees C. Now when we run our problem, so we can see that actually we get significantly higher power output. Instead of 40, we got 71 megawatts power output of the turbine. And looking at our QT diagram, we can actually use the one we already have. Just double click on it, and in contents add another heat exchanger. And we can see that now adding the preheater, we can use much more energy from the flue gas, and yeah, our power output almost doubled. Or looking at the system efficiencies, now we get overall efficiency of 40, almost 50%. However, still looking at the flue gas outlet, our flue gas is at 238 or 239 degrees C, meaning there is still some energy that we could possibly use, and whether we can use this energy in our steam cycle, whether there is still space for it. So actually there is, because here after the pump we have 29 degrees C, and we heat up this water only by taking some steam out of the turbine as turbine bleed to heat it up to our specified 105 degrees C. So let's add another heat exchanger. Now let's do it like this. So flue gas going in and out. And water going from the condensate pump into our heat exchanger, and then from the heat exchanger into the deaerator. Now specifying the heat exchanger, again we need to specify the pressure drops or pressure differences. And now actually it's not, since we have fixed mass flow rates on both sides, it's not entirely feasible to specify the high or low temperature pinch points or temperature differences, but we know that the deaerator is at 105 degrees C, so let's specify that we want to heat up our water, stream number 1, the primary side, to 100 degrees C, just below the saturation level. And EEQ code number 2. So we can run our problem, and looking at the QT diagram, we can add this another component. We can see that there is another part of the heat that we managed to extract from our heat source, from the flue gas. Also the power output increased by another 4 megawatts, and the flue gas entering the chimney entering the stack is now at 207 degrees C. Also looking at the efficiency, so we got slightly above 50%. But is this the maximum power that we can extract from the flue gas with this steam cycle? It depends up to the pressure that we have specified here in the pump. For example, if we put 150 bars, so it's slightly lower, but not much. Let's try 190. And it's maybe a little bit higher. Let's have a look again, about 50%. But if we want to make sure that we maximize the efficiency of the cycle, so we have the function we have a tool for that here in the cycle tempo. So in calculation we can click on the optimization option. Then we will say that in number of apparatus 11, which is our pump, we want to modify the outlet pressure, and starting value, let's use the 180 that we had in there. Now running our problem, we got into an error where after a series of optimizations work, the pressure was gradually increased and increased, but it seems that here with this configuration the optimization function went into the supercritical region where our system would not work very well. So the simple optimization actually wants us to increase the pressure beyond limit in which this configuration of the cycle can work. But let's have a look at one more thing, what this increase of pressure actually brings us. So in the optimization we can ignore the optimization input. Here we have this, for example, height 180 bars, and after running the problem with the system efficiency roughly 50.3%, look at the data for all pipes and find our turbine outlet, the pipe number 10. And you can see that the quality at the turbine outlet is only 78%, which is too low for actual and suitable operation of the turbine. So increasing our pressure is actually not that feasible because we cannot build turbine for that. So for actual system we would need to have pressure lower. We can try, for example, 150 bars. Data for all pipes, 10, already we got 80, but still 80% is rather low. 120, let's try. %. If we put in 80 bars, we still have the 35 degrees there. And now only after putting pump outlet pressure of about 80 bars, so we are getting to the feasible quality at the turbine outlet of about 85%. With the system efficiency actually larger than we had before. So what's happening here? The thing is that the efficiency of the system doesn't go monotonously with the pressure, but there are some local optimums and local minimums. So we can again try to use this value, general calculation, optimization. We put starting point of this 80 bars. Now we want the optimization to run, and we actually get a success with pump outlet pressure of being only 42 bars, meaning 4 megapascals. So our system is at much lower pressure, which means it is all the components are with not so thick walls, meaning lighter, cheaper, and also we've got a maximum efficiency where now the turbine output is almost 76 megawatts. Also we can have a look last time at the data for all pipes, and we can see the turbine outlet has quality of actually 89%, so it's fairly good. And we can have a look at our graph of QT diagram. We use most of the heat from the heat source. Our temperature of our flue gas is only 155 degrees C, and our system is optimized at this point. If we would like to further optimize it, so we actually need to decrease the surface between the curves of the temperature profile of the heat source and of our power cycle. And we can see that probably the largest irreversibility will take place during this boiling. So what we can do is to change the system into the dual or triple pressure combined cycle. But now, with established methodology how to calculate the cycle with single pressure, I believe that you can only do these double or triple pressure cycles by yourself.